Delores, Professor Knipp, served the U.S. Air Force on active duty office and as civil servant for over 30 years. The Air Force sponsored her PhD studies at UCLA, where she studied space environment and the developing field of space weather. During that time, she worked with HAO's Art Richmond to improve upon the data assimilation method for the upper atmosphere, known as AMI. And after a 20-plus year teaching career at the U.S. Air Force Academy's physics department, Delores began a more sustained work with the Boulder space weather community. She's a research professor at CU, Aerospace Engineering Sciences Department, and a senior research associate with HAO. Her graduate students are continuing the development of the next generation of ionosphere electrodynamic and data assimilation methods. And Delores is currently editor-in-chief of the American Geophysical Union's journal Space Weather. And today, she's going to tell us about the 1967 solar storm that is at the root of the modern space weather. So with that, thank you. All yours.
So I will tell you this was a challenging but fun presentation to put together. It's derived from a paper that was accepted in Space Weather. Yes, I know, my journal. But it went through the normal review process and went online yesterday with a press release that has gotten some very interesting remarks via Twitter, that kind of thing. So press releases are not for the faint of heart. But anyway, maybe a provocative title, How We Got to Now, but almost didn't. And that has to do with a story that I want to tell you about really how we got through the Cold War. And one small piece, aspect of getting through the Cold War had to do with this great storm that occurred in 1967. It was a solar radio disruption event that was unprecedented, and it had impacts on technologies that I'm going to try and tell you about. Part of the challenge of making this presentation is that it's not quite the linear, well, we started with these introduction, here's the data, here's the methods, and here's the results. So I have to kind of go back and forth and tell you a little bit about what we know now, what we knew then, what we didn't know then, and how this whole storm formed essentially a fabric for the modern military space environment support system, and to a large degree for a companion to much of the work that's done over at Space Weather Prediction Center. So I will start with this title, or not the title line, but all of the names that you see here in italics are either former military members or former civil servants who were involved in either the event itself. In the case of Al Snyder, he was the duty forecaster in May of 1967 at NORAD Cheyenne Mountain Complex when the event took place. The rest were involved in post-event analysis, either at NORAD Cheyenne Mountain Complex or at 4th Weather Wing, also in Colorado Springs, or at Air Force Research Laboratory, which at that time was called Air Force Cambridge Research Laboratory. And then there are a group of folks on the bottom who helped me keep the wheels on the track as we kind of went down investigating various aspects of this storm, which have been known about for a very long time. But they're in little bits and pieces of various journals, and you come together, bring it all together, and look at the data over 40 to 50 years. You come up with about 40 or 50 references that help you piece together what happened on this day. So what you're seeing here is an image from the archive, the National Solar Observatory. It was actually taken at Sac Peak. It is H alpha, so emission and hydrogen alpha. At that time, 1967, this is just as we were starting to launch spacecraft that could actually look at the sun and see X-ray images, but at that time we did not call these large regions of tangled magnetic field and hence emission active regions. We gave them numbers that were associated with the astronomer McMath. So this is McMath region 8818, and the image was taken by Air Force members, Damascus and Stover. Okay, so the outline goes that I'm going to tell you a story about how this particular active region challenged our security technology in the late 1960s. It'll be an unusual discussion in that we have a little bit of politics that need to come in here, or maybe more appropriately history. There'll be, I'll discuss the solar situation that played into the immediate decisions that were being made, and then go back and forth giving you some kind of a sense of the effects of the storm on heliospace, so outside of Earth's magnetic field and certainly within. And then I'll summarize by telling you what was so great about this great storm. So, without further ado, the story as it develops. So, in the 1960s, and actually a full 20 years ahead of that, the world had become engaged in what we know as the Cold War. And I suspect many in this room have memories of the 1960s and all kinds of discussions about things like the arms race and the space race. But historically, this whole system develops in kind of a national psyche, thinking about keeping the nation secure in the face of surprises. So certainly 1941, Pearl Harbor attack, the Soviets acquiring the technology for the H-bomb shortly after World War II. The Sputnik launch in 1957 rattled a lot of people who in this nation who said, "Oh my gosh, we are so far behind," and that spurred the entire space race that finally put us on the moon in 1960. In the late 1960s. The Cuban Missile Crisis, something that came even closer to home in late 1962. So all of these things were surprises that the military, the industrial complex supporting the military had to think about. And ultimately what came of that, through both pushes and pulls on both sides, Eastern and Western blocs, was a doctrine and a strategy called mutually assured destruction, which is basically everybody has way more nuclear weapons than they could ever use, and the key part of keeping the peace is basically having a sufficient retaliatory capability that if one nation does use nuclear forces, there's a retaliatory capability from the other nation, and everybody loses. So you keep the peace by sheer threat. That's the way it went. Okay, so in the mid-1960s, we are very, very much at the height of the Cold War. There are new technologies that have come on board, so certainly the intercontinental ballistic missiles were a big concern, multiple reentry vehicles, all kinds of technologies, and our nation and other side as well was always figuring out how do we watch out for these. There were also at that time numerous regional conflicts, and the Eastern bloc, Western bloc would pick a side, and then they would kind of go at it in proxy mode. In particular, that was happening in the Vietnam War escalation in the 1967. The demilitarized zone in Vietnam was no longer demilitarized, so troops were going back and forth, so tension's definitely high. There's one other aspect of this that I want to bring up the date because it's important. On the 22nd of May, or depending, where you put the date line, 23rd of May, 1967, tensions were very high in the Middle East. And Egypt had chosen to block the Tiran Straits, which is the narrowest part of the Red Sea, and Israel viewed that as an act of war. So there was a very definite uptick in the tensions at the time. So that's something to keep in mind. So where does that take us in terms of a technology system that might be affected? We had a ballistic missile early warning system that was developed conceptually in the late 1950s, constructed in the early 1960s, first full operational capability 1964, and then the day after full operational capability, the plans go on for the next upgrade. And the next upgrade, which is now off of the screen down here, was accepted as fully functional on 15 May 1967. So now we've got two things going on in May of 1967 that add some interest to the story I'm going to tell you. Basically, what that radar system consisted of was 3 radars that operated at 440 megahertz. Keep that number in mind, it's important. Ultimately, the one over here in Great Britain, Filing Dalesmore, became a system that had a full 360 capability. But I'll just point out to you right now that they're basically looking over the poles to see what might be coming in. So you would think that they could not possibly get a solar signal into their antenna. But that's not correct. They did. What their job to do is to basically have at least 2 fans of energy so that you could detect something coming through, and that could either be a missile, an aircraft, or any kind of space object. So these radars were also used for tracking space objects, space debris, that kind of thing. They fed information into NORAD-Cheyenne Mountain Complex. In the event that something pierced that radar fan, there were alert crews on aircraft, and at that time we certainly had missile crews too, but this is mostly to do with the alert aircraft that were ready to respond to any kind of threat. And as a matter of fact, up through early 1968, we had a virtually full-time aircraft flying with some element of nuclear weapon on board, just to be ready to retaliate in case need be. One of the concerns, there were many concerns with these large radars that could sink into the ice and that sort of thing, so lots of construction effort went into that. But one of the concerns that started to play into the development of a need for space weather support was radio frequency interference. So 440 megahertz is certainly a frequency at which the sun can put out radio energy, and it did. If there was an alert, then crews that were sitting in alert bunkers would dash to aircraft, and they went through these exercises on a regular basis. Just get to the aircraft, get the engines turning, so that might be the next level, and the next level would be get the aircraft to the ends of the runway ready to launch. So, with that, I will just go back to the previous slide and tell you that the Cold War was a very prolonged event. We were really right in the middle of it right here. Here is May 1967, now put up against essentially what we know as the 11-year series of solar cycles. So here's the rise to solar cycle 20. It ended up being, in terms of sunspots, a pretty medium solar cycle. In terms of very large output bursts of energy, it was pretty spectacular. So here we are, May 1967. In May 1967, as I mentioned, there was an incredible region that appeared that passed the east limb of the sun, McMath region 8818. This is a hand drawing of a composite over several days of what that region looked like as it crossed the disk of the sun. And these are the strongest parts of those sunspots. And what you will notice here with this north-south is that within the umbra of these regions we have mixed polarity. So this was a system where the sunspots were actually turning around. They were turning around each other, and I will show you the comments from Patrick McIntosh that says they were colliding. So the gradients in these sunspots, especially in this region right here, were very strong. Patrick estimated 2.5 Gauss per kilometer, which is exceptional. To look at this in a slightly different view, now we have some hand drawings from Dodson and Hedeman. They were at I think it's the McMath Observatory in Michigan, and they tried to draw what was the H-alpha images, hydrogen alpha emissions, of the flares that took place, first one at 1817 on the 23rd of May, and then with these dates. Each of these, in one way or another, they grew successively more intense. Every one of these X-ray certainly the last two produced hard X-ray emissions. Soft X-ray emissions, if we were grading them today under SWPC standards, the first one was an M2, followed very quickly by an X6 and an X2. So we had incredible energy stored up, and the sun was trying to release that magnetic energy. There was extreme emission of EUV based on later input from various observations and analysis. There was even a white light flare that is sitting just right underneath this region here. It was small. It's not quite comparable to, nowhere near comparable to what we think of as the Carrington event, but a white light flare nonetheless. And H alpha, 2 ribbons, so we could actually see the feet of where the particles were being accelerated down into the sun. And of particular note, there were really huge radio bursts, and that is the stuff of the technology that was disturbing to our national security. So I'll give you a sense of what happened. So not only were there great radio bursts, but the X-rays so disturbed the day side, it greatly increased the electron density on the day side in the sunlit sectors, and high-frequency radio signal loss was shown very quickly after the second flare. So this is the 13 megahertz high-frequency measurements being made here in Boulder, and it's on a link between Boulder and Illinois. I can't remember which town in Illinois. But first of all, it's supposed to be kind of a relatively flat, slowly varying signal, and all of a sudden we have these huge frequency deviations indicating that somehow or another the ionosphere, lower edges of the ionosphere, are greatly disturbed. It recovers just in time for the next flare to take place, and we lose the signal again. So dayside radio propagation was greatly disturbed. Dayside radio propagation was what we needed to make sure that we were in constant contact with aircraft, civilian, military, you name it, we needed it. Here's a modern picture, so here let me jump forward to show you what happens when we get an X2 flare. This is from 13 May 2013, similar time of day, and what you're seeing here are all of the ham radio links that are just being kind of tested throughout the course of the day by various interested people. And as the solar flare reaches its peak at X2, what we find is that much of the signal on the day side is not propagating. So dayside HF communications compromised, if not impossible, during this time. So there's technology one that is greatly stressed. The real stress in the system came in with the Great Radio Burst, which is actually primarily part of the third event. There were all manner and means of aspects of this radio burst, but I will show you here. This is 184 megahertz. These blue lines indicate that this time right here is equivalent to this time frame. And at 184 megahertz, that measurement was made here in Boulder, we go off scale in terms of emissions at, I believe it was 6,500 solar flux units. Now, solar flux unit is a measurement that we use to basically say how much radio energy is the sun putting out in a very specific waveband. So at 184, it's off scale. So let us now proceed to 606 megahertz. At 606 megahertz, we had more than 370,000 solar flux units. The norm is about 40. So that's a lot of solar flux coming in. And remember that I mentioned 440 megahertz. Well, we don't have a measurement at 440, but at 606, we are beyond anything that had been measured up to that time. And the papers that I've read said it was an absolute testament to one of the non-commissioned officers at Air Force Cambridge Research Lab who actually managed to keep all of these microwave systems going and functioning so that we could make these measurements and know that the sun really can do this. And it was the sun putting out this radio signal. It was not enemy jamming. You can go down through here on each of these, at each of these different frequencies. I have what is the typical sort of disturbed time. So you can see that this is off the charts in terms of radio bursts, and it was mostly coming out of that second and third flare, which we would now call X6 and X2. But it's the X2 flare, it's the later one that actually puts out the real disturbance. So this is just a whole series of, what does it look like at any given frequency. You can put these all together and then plot against frequency and then look at, what is the peak in terms of the solar flux units. And what we get with the first flare, it says here, tiny print, you have to divide this by 10. So this one really would sit way down here. The second one at, say, 5 megahertz, the number is low, and then it reaches a crescendo up here on the order of, 10 gigahertz, essentially. The third one has a very interesting structure, because what happens is in these lower frequencies, in the 300, 400, 600 gigahertz range, we are virtually in territory not seen. Subsequent, there have been some measurements that show that indeed the sun does put out that kind of radio output, but it's remarkable. So just to recap here, what we saw was, putting it now all together with the radio, the soft X-ray, the hard X-ray, what we were seeing was a wildly disturbed sun that lofted or generated flares. They're called homologous flares because they come out of the same region, and one right after the other. The response in the ionosphere is that the ionosphere could not recover, it could not get back to base before the disturbances from the next flare. So the ionosphere itself got into a very strange state with perhaps as much total electron content, electrons ripped off of their parent atoms, in the upper part of the ionosphere as in the lower, and usually it's just the opposite. So here we are. We have our radars operating at 440 megahertz, and remember I said they're looking over the polar cap. They're not looking at the sun. But this is May 23rd, 1967, so the northern polar cap is in fact tilted towards the sun. These radars had been recently upgraded, fully tested with everything that we thought could the sun or any technology type of jamming could really throw at it. We were, I'd say, convinced that whatever would disturb them would be of an enemy source. But the alert system suspects jamming of some kind. Enemy environment unknown. The alert crews at that time, they basically had 15 minutes to respond, to get aircraft in position if need be. And so air crews are doing that. Okay? In the meantime, there's not much in the way of dayside radio communication, so this makes commanders very nervous because you want positive, definite control of your forces. Enter observations and a very astute group of Air Weather Service Solar Forecast Center staff. The Air Weather Service Solar Forecast Center had been set up in Cheyenne Mountain Complex just 1 year before. It was kind of a long go to get Air Weather Service to move from terrestrial weather forecasting into Cheyenne Mountain, into space weather forecasting. Many of the people officers who were staff down there went through CU Boulder's astrogeophysical department. And so we had a group of forecasters down there that had probably never seen anything quite like this, but they were at least aware that there was a possibility the sun could do something like that. They were seeing, via teletype and secure voice, information coming in from Sac Peak, from Sagamore Hill, from other observatories, although those were the two that were really looking at the sun. They were able to, they had already mentioned in a daily briefing earlier that morning to command staff that the sun was very active and had the potential to put out significant emissions. So they were looking at signals coming in, and they were processing those and going, well, this disturbance, even while klaxons are going off, this disturbance could be coming from the sun. So that information was at least raised through the decision-making process, through NORAD headquarters, and that information was flowing up to command authority in the Pentagon. SAC did not, a Strategic Air Command, did not have a solar support unit at that time, so they're basically just getting support that says, yeah, you're not going to be able to communicate in your HF frequency. So there's a little bit of, well, there was a lot of mismatch there in terms of information that was being provided, but fortunately, these folks were well enough versed in what was going on that they were able to convince commanders that this is certainly worth considering. What they ultimately, so that is the place at which critical observations, critical education, critical resources came in and basically allowed us to make a decision to hold on what appeared to be jamming. Now, you should understand that full-scale jamming, as was being seen by these radars, was considered an act of war. So we were under attack, but it was under attack from the sun, basically. Okay. The documents that I've read, the things that have been declassified, basically said that decisions went to the highest level of government. I will assume that at least that meant that the president was briefed on this. I don't know if the decision to hold stopped here or with the president. President Johnson was very much trying to keep the lid on many political issues at the time and try and reach some form of détente, which was a new terminology that came into play much in the late 1960s and into the early 1970s. So with very rudimentary data, those NORAD solar forecasters were able to let commanders know that it was most likely that the BMU system would be recovering, given no other additional solar bad behavior, would probably recover in tens of minutes to an hour. That the dayside communications challenge, however, would continue because the ionosphere was greatly disturbed, and it was so disturbed that there was, in many cases, in the upper part of the atmosphere, no way for the electrons to get back to their parent ions. The temperatures in the upper ionosphere deltas of 5,000 Kelvin. The polar cap communication outage would soon develop. That was pretty much a statistical forecast, and so I will explain what that means in case you don't know that, and that a major magnetic storm was likely in 36 to 48 hours. They nailed that. It arrived in 40 to 42 hours, depending on which one of these, because which one of the storms hit us, because the sun was throwing out this incredible amount of energy. It was also throwing out mass in terms of coronal mass ejection. The first one comes out, has to plow through the interplanetary medium, but it clears the path for other ejecta to fall behind it, and so they're coming like a train. And they do arrive in that 40 to 48 hour time frame. And so much of what I'll talk about for the remainder is what happened then. What were those other impacts? So I've already told you how it was we got to now. We basically had the right kind of people in the right place to let us know that it was more likely than not the sun that was sort of declaring an act of war. So here's what we have. This is from some writings by Pat McIntosh in a document I believe he ended up writing in the 1970s, but it's the East Limb passage of one of the greatest activity complexes of solar cycle 20. There's collisions between central and western members of the complex, growth and expansion, general bad behavior all over the place. Mergers of leaders and easternmost members leading to delta magnetic configurations, the gamma delta, the famous kind of gamma delta, opposite polarity spots in the great within the umbra. So knowing that, what can we kind of summarize here? There was, at least from the radio portions of these great outbursts, immediate impact on DoD. We had knowledgeable people in place. NORAD was notified in real time, but there were other agencies that did not have a similar type of support and went off to make decisions based on what they knew at the time. This is an interesting statement. I'm still kind of wondering exactly what it means. The environmental effects negated the effectiveness of the detection system. I think it says it's jammed, and had a direct and that jamming had a direct bearing on decisions at the highest levels of government, but equally important was the information that was coming in from the forecasters. The impact of this flare and indeed the subsequent storms provided the necessary force to incorporate space environment data into the Air Force decision-making progress. And this is a quote from a document that was probably never classified, but it was dated in the early 1980s. So, we are here at now. What else happened? Let me tell you just a bit about the geospace and heliospace storms. So we'll go back and we'll flatten out that very first diagram, or very first image that I showed you. It's a little, can we dim lights maybe just a bit? See if we can do that.
I have summer school experience.
And high jump.
High jumping experience.
Could you lift him up a coronal?
Pardon?
Could you lift him up a coronal?
I will do, yes, it is slowly drifting. How about? I will describe while we dial down the lights. So we have flattened the sun, and we have taken images of the central meridian of the sun, and we paste them together, and the pasting in time goes this way. So on about May 23rd, thank you, Mike, I think that's helpful. Yeah, okay. On May 23rd, if we look from the North Pole to the South Pole, actually not quite that far, I think 60 degrees to 60 degrees, is that right, Ian? Yeah. Okay. 70, okay. So what we're looking at here are regions that are shown down here in color through the efforts of Bob McFadden and Ian, who's sitting in the back. They are reconstituting Pat McIntosh's hydrogen alpha synoptic charts. And what we're seeing here is a region of incredible complexity in terms of bits and pieces of closed magnetic field lines surrounded by open magnetic field lines, surrounded by filament channels. And in the middle of this, we have this intense set of essentially 4 groups of sunspots whose polarity is intermixing. And we blow it out over here, and you can see that some of those spots seem to be sitting in open regions, close to open-closed boundaries. Others were within those closed boundaries. That is part and parcel of the complexity of this system, and they were colliding and rotating around each other. To view what likely comes from that kind of configuration, let's just take, I'm going to borrow a graphic from the HAO Space Weather Summer School from Sarah McAllister. And we look now at the beautiful images that we can get with Solar Dynamics Observatory, and we can actually see the magnetic fields that might be anchored in those oppositely directed sunspots. If those sunspots are twisting, merging, participating in all kinds of dynamics, then the magnetic field grows stronger and stronger in these regions. What will ultimately happen is some of these fields will twist and writhe. They will try to reconnect or merge in a way that reduces their magnetic complexity and their magnetic energy. and that's shown by this region right here, which is the magnetic merging region. What happens there is magnetic field can be converted into almost pure energy that can go off as photons, or it can go off in heating, or it can go off in accelerating charged particles, some of which go barreling out into the interplanetary medium, some of which get driven down into the solar atmosphere. And as those particles are driving down into the solar atmosphere, they're interacting with with a richer environment, a higher density, and so additional ionization takes place. There's X-rays being generated here. In the case of the really violent flares, we essentially begin to see in these regions emission of soft X-ray, deeper down hard X-ray, in some cases even white light. And this was a case of there being a population of energetic particles, probably between 40 and 100 keV per particle, that would be needed to generate in these little images, or little spots right and down here. We apologize for the inconvenience. Well, that's bad. Recover the work when you restart. All right, let's see if we can do this gracefully. Open, recent. Okay. Well, all right, fair enough. Where were we? We were rudely interrupted by Microsoft. Let's try this. Are we there? All right, we're back. So, here we are. We're now looking down at a cartoon that is drawn by Svetka. Started working on this in 1970, 1972. And he is essentially showing us what that region where we have the mixed polarity looks like. Right in here we have a neutral line between southern and northern poles. It is along this neutral line, actually on either side, that we see the great H alpha emission that eventually blew out to take up 12 square degrees of the sun. On top of that is what he called it hot condensation, but in fact what that is, we're seeing those are the beautiful arches and soft X-ray that sit over those two ribbons of particles driving down and creating H alpha light. And then he was able to locate, and the images were made both here in Boulder and at Sac Peak, the places where the white light flare. It was a rather small region right in here where there was very concentrated particles coming down. So we're going to take that a step further. We'll just look at it again. So we tilted this on the side. Here are these particles coming down. This is a magnetic loop. We've got accelerated particles coming down. There may be hard X-rays, even gamma rays down here near the surface of the sun. But in that same area, as those particles come down, what we start to see are places where radio emissions can escape. There is certainly plasma that is being accelerated here. These are moving charges. Moving charges create electromagnetic waves in the radio portion of the spectrum in this case. In these regions right here, where you have particles kind of caught in a magnetic bottle, they can be radiating in radio portions of the spectrum by gyroresonance. And so they are also giving information about, hey, I'm here, in the sort of 2 gigahertz range and above. So, there, I said it, gigahertz radio bursts. In addition to all of that activity that was going on, there is no doubt that at least 2 and probably 3 blasts from the region where the merging takes place of coronal mass is blooming out into the interplanetary medium. And blooming would be a gentle word. It is blasting out at, I think the general thought was that this was a system that may have started in the several thousands of kilometers range as it moved out from the atmosphere and ended up striking Earth in the 800 to 1,000 kilometer range. So it was not particularly fast CMEs, which is probably something that saved us. As those structures bloom out, they are doing several things. They are, if they're fast enough, creating shock waves that then can then accelerate other particles, and that was the case in this situation. So at this front of these magnetic coils that you see here is an interaction between those magnetic fields and particles in the interplanetary medium, creates shock waves and very, very energetic particles, which will also come barreling towards Earth. So what we have here now is we know, amazingly enough, that we had Explorer 33 with the very first, I believe it was the very first X-ray measurements. We now know that those there were at least 3 flares. Interestingly enough, this measurement was made by James Van Allen. So he was into X-ray measurements at the time. So the flare response that comes with that is basically to enhance the density of the electron density in the ionosphere, in some cases in the lower edges by as much as 300%, meaning that radio waves that are trying to propagate through and bounce off of these are probably being absorbed rather than bounced, and so radio propagation essentially stops. Liang, who is from here at HAO, has actually modeled what would be the effect of having some of these very large flares versus a flare that's off on the side of the sun. And she has shown that these center limb flares are very effective in producing the ionization and the long-lasting effects in the ionosphere that we know were present at that time. Additionally, besides the flare sequence itself were these energetic particles, some of which may have been coming from the flare, some of which may have been coming from advance of the CMEs. You can see that this is a 10-day interval, and when we look at the levels of the 10 MeV particles, that is where Space Weather Prediction Center sets a threshold, and we are here well above threshold. I believe the number is 10, and so threshold would be around there. This measurement was made by Explorer 34 that was launched into this energetic particle storm on the 24th of May. Of course, we would never do that now, but we did it then, knowing no better, and got these amazing measurements that tells us that we were basically at least a S1 radiation storm level for 7 days straight. So polar cap communication, this is what the SWIPSI product that is for some other day, 2015, but basically shows you where polar cap communication may not be possible in the HF portion of the spectrum, and it constitutes a very large piece of real estate. Now, admittedly, this is flattened, but it covers a lot of territory. As I mentioned to you, the Sun-to-Earth transit times for the coronal mass ejections themselves, for these events that probably left on the 23rd from the Sun, 40 and 41 hours, and then there were other events. There were other active regions, so this was not the only one. So to kind of give you a geomagnetic summary, we didn't have a lot of interplanetary measurements. We do know from some sparse hourly measurements that the solar wind densities were up. The KP index pegged at 9 and stayed at KP at least greater than -7 for 27 hours straight. The DST index hit -387. That puts it in the top 8 of storms recorded since the DST index, which is a measure of magnetic disturbance, has been made. And let's see what else. This is the measurement of the Forbush decrease. So essentially, how effective were these huge blossoms of energetic coronal mass ejections in shielding us from cosmic rays? And there was an 11 to 12% decrease in the south pole counts of cosmic rays. So we were being nicely shielded from cosmic rays at the time. Be thankful for that. The predecessor to Space Weather Prediction Center was making measurements and forecasts at the time. They have some very interesting things here. So we still have a severe magnetic storm in progress that began at 10 UT on the 25th, so about 40 hours. Large flares are still possible. We've got Aurora visible over Fort Belvoir, Virginia. Now we have Aurora reported as far south as New Mexico, and the storm goes on and on. We get to see where the Aurora were reported, kind of expected places, but a very deep southward kind of turn. And what we know from the Auroral Electrojet Index is that it appears that there were great pulses of activity. I'm still looking to find out if there are any records for this part of the nation. I can't find anything. Aurora were seen in Central Europe, and then in Alabama, Georgia, and in New Mexico, but we have kind of incomplete records. So getting a little closer to what we have here, I will tell you that there were huge perturbations in the amount of total electron content during this storm, and as of 2005, it stood as the largest negative phase ionospheric storm on record. That may since have been succeeded, but it was basically, as far as some systems were concerned, the sun never rose on the 26th of May to start creating ionization. Other records indicate that as far forward as 3 months, there were significant disturbances in the inner radiation belt. So whatever happened caused such a crush of the magnetosphere that there were disturbances in the inner radiation belt. There were magnetopause crossings that lasted for at least 3 hours on the afternoon side, virtually unheard of. This was our first geosynchronous spacecraft that was making these measurements. Happened to be at the right place at the right time. We can estimate, because it had a magnetometer, that in the magneto sheath, out ahead of the magnetopause that was crushed in, the sheath field reached minus 160 nanotesla. So that divided by 4 would be an indication that it was probably a minus 40 or 50 nanotesla southward storm. And then I think the last thing that I really want to try and emphasize was that there were huge effects in the thermosphere, tremendous amounts of energy coming in, not only from the solar photons, but from the interactions of currents and Joule heating. And we had measurements. We saw at all altitudes at least 500 Kelvin global temperature increase within 6 hours. And then the atmosphere suddenly went into cooling mode and overcooled. It is a circumstance under the biggest storms where the thermosphere fights back, because chemicals are made in the thermosphere that allow it to radiate furiously in the infrared and actually overcool. On the 22nd of May, we had put on orbit a satellite, DoD satellite, that was to measure acceleration. It was the low G acceleration satellite system. Its apogee dropped 100 kilometers in 4 days, and I believe after 5 days it made no more reports. That was the end of that. We know from contributions to this paper that half of the NORAD catalog, in terms of things that were tracked, had to be reacquired in the subsequent days and weeks. So I will tell you just one more thing. As I mentioned already, we had a great disturbance in the heliosphere, and meaning that these billowing magnetic fields and their associated mass essentially shielded us from the cosmic rays that were coming in. And this is a very substantial drop that goes on for days and days and days, and essentially takes us out well into the middle of June before we recovered. So you probably guess I think this was a great storm. What was so great about it? So let me summarize. This is part of the table from the paper. We had more than 370,000 solar flux units at 606 megahertz, very close to the operating frequencies of these radars. We don't know what those measurements were at 440 megahertz, but let's just say it was bad. Even at our standard F10.7, which we measure every day to kind of monitor sun, typically on a peak we get 300 solar flux units. We had 8,000 during that second flare. Solar energetic particles stayed at an excited level for well over a week. Extreme KP, geomagnetic disturbances. Let's see, I think I've probably already said all of these. The bottom line, and the point that I really emphasize in the paper, is all of these things happened, and we can, write about them in our science journals. But the primary thing that I think that makes this great was this storm and its intersection in terms of politics and our national security, and the recognition that we needed to put more resources into space environment support services, and that we already had that in place to at least a small degree, and that was a critical piece of getting us to now. The one thing you might notice that's not there, there is no mention of geomagnetic elite-induced currents. I cannot find a single instance that says that there was any problem with the power grid. Nothing. I'm still looking. Okay, so I will take questions, and I will happily acknowledge many people who have contributed to this, and not the least of which are some military colleagues without whom we would likely not have made it to now. Yes.
Thank you very much. All right, time for questions. Yeah, Bill.
Yeah.
Oh, that's a great story, Delores. There's something else missing up here. Tell us what you know about the Soviet side of the reaction and your defense and development of space weather observations.
Not much at the moment, but I have one story, and I believe with the publication of this paper, I'm really hoping that we will get more. But one of my colleagues of Russian origin at the National Solar Observatory told me that in 1979 he had a conversation with Neveshev, who is one of the great solar astronomers, and at the time of this event was apparently in charge of a large number of solar observatories. And I believe the way it was worded was that this event funded a lot of solar research for a very long time in the Soviet Union. So that is a secondhand what I know. I will tell you that I have been getting, requests from the press for 36 hours now. It seems like longer than that. And I do have a request sitting in my inbox from one of the reporters from Russia. So who knows? Maybe I'll know more soon. But I'm really hoping that this will engage a much broader input from the international community to study this great storm. Clearly, this is kind of a blinders on, but sometimes you have to focus in order to figure out what's important. So this is what we have at the moment. Yes.
So it sounds like the radio communication globally was wiped out.
Perhaps not on the night side.
What I'm wondering is, was the White House able to communicate with the Soviets via landline, or was that knocked out as well?
I would assume that those landline communications were still fine. I don't know. Looking back at the kind of press releases and things that were coming out of the White House at that time, the only thing that came out on that day was a comment on 23rd of May, was a comment from President Johnson about the concerns he had about the developing Arab-Israeli conflict. So absence of information does not mean there isn't information. It just wasn't high enough on the list, or maybe it was a security concern. So, but during the primary portion of the event, I believe it was primarily a day-side event. Once the coronal mass ejection and the geomagnetic storm came in, then the auroral zones were disturbed, and probably all other forms of radio torture that the Earth's atmosphere can endure were involved. We did lose communications in the polar cap, or they became very patchy, and that probably only took about 5 hours. So polar cap was also not good. Yeah.
It sounds like the emissions, the ejections and all, hit the ionosphere, and there was a lot of radio interference from the radio emissions also. So it sounds like there was both RFI interference and absorption from the ionosphere, right?
Both going on at the same time.
Okay, so what's the simple physics behind the absorption in the ionosphere of HF radio?
Okay, so what happens is those, primarily the X-rays, penetrate much deeper in the ionosphere than most of the solar extreme ultraviolet, which is the extreme ultraviolet as the energy that we see kind of as background the whole time. There's some amount of solar X-ray, but with these flares, the solar X-ray output can go up 3 to 4 orders of magnitude in a matter of minutes. When that happens on the day-side ionosphere, the material that makes up the upper atmosphere has a relatively small cross-section for that and does not absorb that very effectively. So those wavelengths penetrate very deeply into the, and essentially lower the lower edge of the ionosphere. Sometimes to the point that the lower edge of the ionosphere is so deep in the Earth's atmosphere that as radio waves attempt to go up and propagate or reflect or refract off of those regions, those radio waves are interacting with so many extra free electrons because they've been created low in the atmosphere that and those electrons then are colliding because we're now in a thicker atmosphere, that the energy of that radio wave is essentially lost. It goes into heating the lower ionosphere and no signal bounces. Or, yeah, simply put. So it's a very tough situation, and deviations in other frequencies as well. So it's probably still one of the great operational concerns is still forecasting, what kind of propagation you're going to get. Yes.
I read once that there was a big solar event in 1859. Was it?
The Carrington event.
And how does this? Is there any way to compare this with what you think happened then?
I would dare to say that event was probably of a whole order of magnitude, just in a completely different class, the 1859 storm. Of course, we did not have radio technologies then, so we have no way of measuring what was going on there. But that event, just from the size of the flare that was described by Carrington, was huge. And we do know that the coronal mass ejection from that got to Earth, was it about a day? 17 hours. So, of course, we had no upwind spacecraft at that time. So it just came as kind of a complete surprise. We know that the Aurora were seen, all the way down into Cuba, Venezuela, I believe. So this one is, kind of a 10% of that. The effects of this one were as much from the geophysical variation and also in terms of the impact that it had on the technology that we knew was vulnerable, but having done the upgrades to the BMUs, we thought, well, we've got that covered. Not. Yes, Fran.
Do you know how Jim Van Allen measured the X-rays back then in 1969?
I do not. I have not looked deeply at the paper. I don't. Yeah. His comments were, because we had not measured X-ray flares before, that this was the greatest flare, of to that point, which didn't say much, but an X6 was, that's something that you get a couple times a solar cycle, maybe. So it's, it was a substantial event. But yes, and to his credit and the credit of many other folks, they managed to keep all these systems operating and making measurements, except when you just didn't have a signal to make the measurements. No, just due to launch and you know, let it go, see what you get. And we got beautiful measurements. It confirmed there were actually two curves on that solar energetic particle, and it just nicely lined up with measurements that had been made before. So very nice confirmation of just how strong those events were, and they just kept coming.
So are there examples of CMEs that lead to large geomagnetic disturbances in the KP index that do not induce ground-induced currents? I mean, it's possible this thing perturbed the magnetic field, but it did not.
What you really need, at least the papers that I have read recently, indicate that you need really, really high speeds. That is the thing that really helps with the induction of the geomagnetic currents. This one does not appear to have been particularly speedy, and now admittedly we have huge gaps. So maybe it was, but given that the Aurora didn't end up any further than the southern tier of the United States, makes me think it was not that severe, rapid change. Do you have any thoughts on that, Tom?
Well, the 89 event took 54 hours to propagate, so that was pretty slow too.
Yeah.
We had huge currents in Canada, so yes, this also had currents that we just don't know about.
It may well be, and maybe those will come to pass. There's one comment out of Great Britain, but I looked at the numbers and I go, nah. But there's yet to come, and we do know that the magnetosphere was oscillating, huge VLF oscillations being measured in Japan. So there was something going on, and I'm sure we haven't seen the whole story on this yet. John? Yeah, so we think it was at least minus 40, and we know that it was that way for probably 12 to 18 hours. I am hoping that ATS-1, which was the spacecraft that was actually measuring the magneto-caused compression, might actually be able to give us some information on that when it went to the night side. But those records are all paper, microfiche, if they still exist, so sounds like something a grad student should do. But not my grad student. Ian? I don't know that there weren't. I just haven't been able to find a record of them. Mm-hmm. Yeah, there are probably many hidden aspects of this storm.
So you mentioned that NORAD had to reacquire a lot of satellites in space.
At least their locations. Yeah.
So how much of an increase in satellite drag did this event cause compared to normal?
I don't know the answer to that yet. It was only late in the study that I actually became aware that the records existed, that Aerospace Corporation had been involved in the launch of the LOGAX satellite, and I'm still trying to get records, but based on what my colleagues have told me at NORAD, having to reacquire half of the spacecraft is substantial. It's not that we had so many of them at the time, but our technology to figure out where they were and figure out what their orbits were, that probably took a tremendous amount of time.
Sounds like there was a lot of drag.
Yeah. So what happened was, well, we know the temperature went up 500 degrees, so that implies a huge expansion. But it was very odd, and it went up and then it sank in terms of temperature, which also meant that the thermosphere collapsed. It's a phenomenon that I've actually been working on to understand how the thermosphere can kind of fight back, and it's able to do that under some circumstances.
One more question, Ricky?
Yeah, were there any effects, I guess, in public, like radio, TV, anything of the storm of this size, I think? Technical effects?
You know, I've been doing the standard Google searches, I will admit. I'm getting ready to go back to my hometown in Missouri and to the University of Missouri-Columbia over the weekend, and I'm actually going to contact the State Historical Society there and see if we can come up with any records of that. But at the moment, nothing that I can see, nothing that seemed to be particularly alarming. One of the Washington papers comments about the Aurora, but it just didn't seem to be a big impact on the U.S. general public.
Did HAO have much of a role to play in this?
There were certainly there are a couple of papers. Kim Melville, does anyone recognize that name? Wrote a paper on this, on the magnetic field, the gradients. And there was there actually was a young doctoral student named Art Richmond, who happened to be my advisor, and he is here. And he actually did quite a very significant part of your PhD dissertation was on the magnetic perturbations at the ground that were caused by the enhancements of the dayside currents as the dayside is responding to all of these flare impacts. So, and you were able to kind of sort out, what, 2 phases of that response? I've read enough of the paper. So that is what I know. I suspect that there were others, but I've been trolling through all kinds of documents, and some have probably escaped me.
Any more questions?
Bill?
What's the frequency of this magnitude of storm? Is it once per cycle, once per 10 cycles?
There's a study by Nita and colleagues out of New Jersey Institute of Technology. This looks like it was a top 1% storm. So it's 3 sigma. That's about all I can tell you at this point in terms. What you need to, there's a very interesting paper on ArchiveX right now suggesting that a way that you can get these extraordinary bursts of energy in the lower frequency part of the spectrum has to do with essentially evacuating a part of the chromosphere where the magnetic fields are still very strong, and then having very, very high alphane speeds. And that ultimately that will feed into these very large fluxes, radio fluxes at these lower levels. But you know, that's one of, I'm sure, many theories. But they have some really nice graphs and some calculations that suggest this could be a part, and it would make sense. I mean, if that was the third of the flare, the third flare puts out most of the solar radio energy, so you have evacuated probably some regions of the sun. So, possible. Bill, one last question. Thank you.
I think that's
All
true.
right.
Well, thank Delores again.